Okay, so this is a frequent error that I see people making, that there isn't as much appreciation for the differences among these four quantities. So again, you've got some container and your fluid is flowing into the container and it's also flowing out of the container. So there's a certain amount of that fluid that's held up in the container. So just by virtue of the fact that the exit flow rate is not infinite. If you are feeding in at a certain rate, then you'll get a certain amount held up there, and there's a certain rate at which you are also removing material there. And then there's a certain initial amount of material, and then there's a certain flow rate in and a flow rate out. These four are very different quantities, right? And I know everything I'm saying now sounds totally obvious, but it is something that there are frequent problems around. If we were to plot with time the change of the number of moles in the container, then the initial amount here will be Na0. And at current time t, let's say current time t is there, then there will be a certain amount in the vessel. So let's say that's current time t. So currently at t, we have an amount Na here. So that's the current holdup that's in the vessel. We used to have an amount Na0 in there. So we started out with Na0. So that's that quantity. So we can't see that currently in this drawing because we are now at time t where it's not Na0 anymore. And this amount is different to this amount. So this is the flow rate in, it's 5 moles per second, maybe. So let's say that's 5 moles per second. 5 moles per second. And maybe Na0 maybe that was 50 moles. So the units are, of course, different. This is 50 moles. And maybe currently this is 25 moles, right? So 25 there. And maybe this is 3 moles per second. So maybe we aren't withdrawing as much as we are feeding. So I'm just putting these numbers down to emphasize these are all different quantities. And very quickly, we'll come to differential equations and differential balances. And if you don't have a grasp on this basic thing, it will seem totally confusing. So just remember, the flow rates are very different to the holdups. And in the holdups, you have a distinction, you have the time variable. There's a difference between the initial amount and the current amount. And that's different to the inlet flow rate and the outlet flow rate. The confusion sometimes comes in with textbooks having similar notation. So for the inlet amount, sometimes they write it as Na0, meaning the flow rate in, the naught being the inlet amount. And in fact, the inlet is often a kind of age 0 type of thing. So there are reasons for some confusion later on, which we'll also talk about, but just start with that. That's a very basic thing. So don't get this wrong. Okay, any questions on that? Okay, so moving on, the basic definitions, you've worked through this. For your convection flow, we've talked about all this, and we've talked about volumetric flux and velocity as a volumetric flux, and we've defined the mass flux and the molar flux. And we talked about all this in the context of convection, so the bulk movement of your fluid. Then we started talking about, what is it? Yeah, so this is using the notation a bit more. So that's, yeah, in terms of bulk movement. And I think one was convection flow and the other one was convection flux, right? And then diffusion flux. So towards the end of the last session, we said just by virtue of Brownian motion and the fact that you've got a space with different amounts of things, then you've got perhaps a high concentration in one region compared with the other region. And so overall you'll see a bulk movement from the one to the other. So if you've got many of your species in the one place here, and you've got far fewer in the other space there, then we'll have a certain bulk movement. Overall, there will be a tendency for us to move from the left to the right there, right? So your bulk movement will be like this. And the way we view that in terms of the in terms of our formulation is to say, well, on the one side, we've got a certain concentration. So if we look at this as C1, right? So if we say C1 is more than C2, and we have X1, so we have position X1 and position X2, then we can define the gradient as or an approximation to the gradient dc dx. That is approximately C1 minus C2 over, of course, X1 minus X2. And so if we look at that, you can see that this is going to be negative, right? C1 is more than C2, but X1 is less than X2. So if X is in this direction, if X is increasing in this direction, then X1 is less than X2. And so this is overall negative, right? So your concentration gradient is negative if we count X in that direction. And so when we define our diffusion flux, we write it as JD is equal to minus the diffusion coefficient D dc dx. So the minus doesn't have anything to do with the diffusion coefficient. It has to do with the gradient. Our diffusion is always against the diffusion gradient. In this case, the diffusion gradient is negative, but we have the diffusion in the positive direction, right? X is increasing this way, so we regard this as the positive direction. So our bulk movement, our diffusion flux is in the positive direction, even though our gradient is negative, right? If C is high here and low there, then C is decreasing in this direction. So that's why that minus sign. Okay, so that we talked a bit about this last time, Fick's law, right? And so if we have this, right, so we can see dc dx, perhaps we can get, maybe if this is a pipeline, we can measure concentration here, and then we can, so if we have some kind of probe and we measure here and we measure there, then we can, and we measure the distance between those points, we can see we can get this dc dx. The other thing we'd need is the diffusion coefficient. And if you look in the notes, we do have ways of estimating the diffusion coefficient. So we'll just have a look at that just now. So there's a bit of work to do to estimate the diffusion coefficient or diffusivity, but in principle, we can get that through a calculation. And then this, as we've said, we can measure. So we can actually estimate the molar flux due to diffusion, right? So we've got the diffusion flux, and then that means we can estimate if we were to choose a certain cross section. So let's say we stuck in a 2 centimeter pipe over here. So we've got some pipe that is maybe withdrawing material. Then we can actually estimate how much of this component is going to diffuse into this interface here. Of course, sticking in a pipeline here will cause other kinds of hydrodynamic influences, but by the end of the day, yeah, and it will upset the diffusion profile also. But anyway, assuming that there are no influences like that, we will have a certain diffusion flux in this direction, and we can estimate how much is entering an area like this. Okay, so that's the basis of many things that we will do in the coming weeks. Okay, and then in the chat, there's a question, what's the difference between X1 and X2? So if you look here, we have a certain position here, X1. So we are defining X in this direction. So maybe X1, maybe this is at the position 1 millimeter into the tube. And then maybe X2, right? So that's the position X1. And then for position X2, maybe that's here. So here's X2. So X2 is maybe 5 millimeters in this case. So it's 5 millimeters minus 1 millimeter. That's the distance there. Okay. So yeah, it's not just a sketch of arbitrary values. We have to specify the exact numbers, right? If you want to know the diffusion flux over a certain space, you have to define the width of that space, so X2 minus X1, and you have to define the concentration at those exact positions as well. So everything we'll do will be quite exact because the balances we develop will be on differential elements. So if you make even a small mistake at the differential scale, when you try to use the equations to predict what the reactor will do, you'll have very low accuracy estimates. So we have to be quite precise in everything we define here. Okay, any other questions there? So coming back here, we can say that the molar flux is proportional to the concentration gradient or minus the concentration gradient. And then we can estimate the actual molar flux through the diffusivity. And then let's have a look at the notes on diffusivity. So let's see. Actually, I don't think I shared that yet. Let me just put that across. So in terms of diffusivity, we have a number of correlations available to us. Okay, so this section, it's a fairly extensive set of notes on this, but I don't really intend going into the, exactly what each of these correlations mean and so on, because we are not actually trying to, how can I say, get into the physics of how you estimate diffusivity. So in our case, in terms of this course, Chemical Engineering Fundamentals, it's sufficient to view diffusivity as the proportionality constant that helps us get to the molar flux if we have the concentration gradient, right? We can imagine a couple of things. So maybe we can just imply a few things about what we expect about diffusivity. So we can expect, for example, that if we were to increase the temperature, right? Let's say we increase the temperature in this pipeline, then we would expect that the molecules would have more energy, right? By definition of temperature, raising the temperature means you are increasing the vibrational energy of these molecules. So they are simply moving around faster. And so we expect that the molar flux will increase. Right, so that is something that we see. So if we look at some of the methods for estimating diffusivity, so looking at this textbook, one of the correlations says that diffusivity has that relationship with the temperature. So it's T to the 3/2. So it's better than simply linear, right? It increases on the order of T to the 3/2, so it's quite sensitive to temperature. So definitely your diffusion flux and your diffusivity increase with temperature. Then you will also see other influences more related to the structure of the molecules. You'll find here the molar mass. So it's inversely proportional to the molar mass. So if your molecules are big and heavy, then of course you would expect they are less motile, if you can use that term with molecules. So your molecules are their movement energy, they have there's more of a barrier, more inertia. So the higher the molar mass, the lower the diffusivity. And then you have some other values that relate more to the molecules and how they interact. So when we talk about diffusion, it's always about some molecule moving against some other molecules. So in this case, in this set of notes, we are writing them as the diffusion of molecule A against everything that's not molecule A. So A star, everything besides A. So you could have a multi-component mixture. You could have 5 or 6 species, let's say, in some mixture, and we want to know how fast is A diffusing through those other components. So that's one summarized way of looking at it. So we always think of diffusivity as a kind of binary thing, right? A diffusing against something else. So in this case, it's A diffusing against a whole mixture. Quite often we do it on the pure component basis. So A diffusing against some specific B. So there is some mixture diffusivity, A against a whole mixture. And if we have diffusivities of A against each of the species in the mixture, then there are so-called mixing rules that help us translate that into the mixture diffusivity or the effective diffusivity. So yeah, this is another interesting one, the Leonard-Jones diameter of the molecules. So if you look at the size of the molecules, the effective size, because of course these molecules are spinning and things like that. So the effective diameter of these molecules, those have been estimated, and the average of the two, so the diffusivity is inversely proportional to the average diameter between the two molecules that are diffusing against each other. So that's in principle how we get to diffusivity. And it is an interesting topic. So if you'd like to get into the physics of how diffusivity, how these correlations were developed, you can go ahead and follow the references in this set of notes. But for our purposes in this course, we'll largely be regarding this as a kind of correlation that we have to use to get to a number for DAB. And you should note that it does depend on the nature of the fluid. So for a gas, there's one set of correlations. For a liquid, there's another set of correlations, right? And so in the setup notes, you can have a look at which correlations are suggested for which situation. And also, you've got all the parameters available to you. And then, straight from the textbook, there are some examples about how to go about doing the calculation for them. Okay, so that's your diffusivity. Any questions or comments there? Okay, and just a second, I'll be back in a second. Okay, so that's our diffusivity. And you can see it has units of meters squared per second, right? Quite often reported on square centimeters per second, but the SI units meters squared per second. So you can see that that's so when you look at the equations. So if you look at the units of flux, right? The unit of flux, it's moles per second per square meter. And then the units of dc dz, right? C is moles per cubic meter. And then you are dividing effectively by meters here. So this is moles per meter to the 4. So you've got moles per square meter per second here, and here's moles per meter to the 4 per second. So left over is meters squared per second, right? So that's diffusivity. Right, so that's the basic setup. And here we are just, here's a nice example where we are looking at diffusion across a 2-compartment cell. So here we are saying, if we have a cell where initially we have our 2 species. So let's say we've got a cell here or a container that's partitioned into 2 cells. So we have a partition here, and then we have our molecules sitting in each cell, and we've got a difference in the concentration. So we have a high concentration zone here and a low concentration zone here. Then we can imagine that once this is removed, right, if we were to remove the interface, then suddenly you have a very sharp gradient, right? If you were to draw your concentration gradient, then it would look like this. So you would have a high concentration. So this is talking about T naught now, right? So the instant you remove this barrier, right, at the instant when you remove the barrier, you have a high concentration here. So it's discontinuously high, and then a low concentration here, right? So this is at T equals 0. And then if you consider a short time after that, so let's say after 1 second, then what will happen is right next to or at the position of this interface, you have exposure of a region where you've got high concentration and low concentration. So this region is where you experience the highest concentration gradient. So you've got a high gradient right here. If you look inside here, you have no gradient, right? Even after 1 second, there's no gradient difference between all the points here. So in here, there's no gradient. In here, there's also no gradient. So there's no net transfer of molecules. Of course, the molecules are still bouncing around in there, but there's no net movement, right? Whatever bounces in this direction will bounce out in that direction also. However, at this interface, you've got a high concentration here, and what will happen is some of the molecules will start diffusing in to the right. And so you'll get a reduction immediately to the left of this point, right? So just to the left, you'll start losing molecules as they start going to the right. And so this will start to drop. And then immediately to the right of this interface, you'll be receiving molecules into this space. So you'll be getting molecules rising here. So that's what it will look like at T equals 1. So I'm just going to call it T1. And then what's going to happen at T2, let's say, is now you are starting to experience a concentration gradient at the interior of this fluid as well. So here now, molecules here are seeing a lower concentration there. So if you compare molecules here and molecules here, then there is a concentration gradient that's experienced. So this will also cause some diffusion further into the cell here. So this cell at T1, points around here were not so affected because they were far from the point where there was an actual gradient. But now after T1, there is some exposure to that. And then at the interface, we have further reduced. So we've also lost more of these molecules to the other side. So that's gone down as well. So at T2, it's starting to look more like this, right? So there's T2. And then you will still get positions where it's so far away that it hasn't seen any differences yet. And then that just keeps happening over time, right? So you can imagine at the next instant in time, you'll get further penetration of the molecules into the other side. And then, of course, as this keeps happening, you are losing molecules of A from the one side and gaining them in the other. So what's eventually going to happen is it's going to equalize and you'll end up with the flat gradient, and that's kind of the new cell there. Right, so that's the process that's going to happen there. Any questions or comments on that? And so we can estimate the rates of all of that happening, because here in this example, we are given the concentration. So, well, they are just defined here. We'll see in the numbers just now, we do give numbers for them. So we define the two concentrations. We have this membrane here and then the diffusivity, and we can sketch the profiles as we've done, but we can also derive the equations for the rate of change of these concentrations. So we know that the molar fluxes are defined this way. So we've said from Fick's law, we can get a molar flux like this. But now we actually want to do a mass balance. So it's not enough just to define a flux. A flux by itself doesn't do anything. We make it useful by developing a balance. So if we look at our cell, we can say, okay, in this cell, what is the rate of change of the concentration in that cell? So let's write a little balance on that. So we can say here, I have a cell which has a certain volume. So my cell's volume is V, and the area between the two cells we can define as A. See, I'm not getting a big balance, but okay, that's fine. So A is the interface area. And that's another thing to watch out for in this course, right? You have to be quite precise about what area and what volume you are referring to. So, for example, the volumes of the two cells could have been different. And also the areas, there are multiple areas to think about. There's an upside area here, there's an area of this wall, there's an area of this wall, there's the area of the entire container, but the transfer is across this interface. So the interface area is the thing that matters to us. So, and sometimes we use subscripts to help remind us about things like that. So AI, although we maybe, let's use capital I. So the interface area. So we can say that in cell 1, for example, the rate of change of the moles there, right, dN1 dt of component A. So we can say in cell 1, component A, the rate of change of the moles there must equal the molar flux at the interface. So we can say N sub A at the interface. So here again, to be quite precise, we have to realize that there are many, many fluxes going on here. right? You can define a flux in here, for instance, and we said at T0 that flux would be 0, but it still exists, right? Even if it's 0. So we want to say quite carefully that for cell 1, we are now talking about this interface. So because mass is being lost in this direction and it's being lost through this interface, we have to say that the flux we are referring to is the flux immediately to the left here. And that's different to the flux immediately to the right there. Well, actually, it's not different to the flux, but a different concentration applies, right? There's a certain concentration up here and there's a certain concentration down there. And they are actually at the same X position, right? And by that, I mean X position, not X position like what I'm doing, X position. I don't mean that, I mean X position, right? So anyway, so to specify this quite clearly, we are going to say this is at the X position, X equals X interface, and we're going to call this X interface minus, right? So X interface minus, it's telling us that, let's just make this bigger. So that's telling us that there's a certain flux at the interface on the minus side, right? So there's a certain flux on that side. And then, of course, we imagine when we do the balance on the right-hand side, then we'll talk about the flux on the X interface plus side, right? So anyway, on cell 1, we talk about X interface minus, right? So the molar flux there, and then we multiply that by the area of that interface, okay? And we estimate this flux by taking the gradient there. So we know that the gradient at that interface, so NA interface minus, that's going to be minus D sub AB. And by the way, something I didn't say enough of is that we assume that there's some other component, some component B that we are diffusing against. So we are not talking about a pressurized zone and a lower pressure zone. It's not that transfer. We are talking about the same pressure, the same density if this is a liquid, and it's just that component A is diffusing from the one to the other. So we are focusing on density. This is not about pressure becoming equalized, although you could say that the same kind of picture would apply for pressure. But that's not what we mean. We mean the pressures are the same, and then just due to the Brownian motion, A is diffusing there. So that's DAB, DC, DCA, DX. And we should specify this is DCA, DX, and this is all at the position XI minus. Okay, so this we need to estimate, and we need to write these as, we need a certain finite gradient here. So actually, there is no gradient. There's a zero gradient here, not zero gradient, there is a zero thickness here once you remove the interface. But the way that this problem is actually posed is that we are diffusing through a permeable membrane. So it's a bit different to what I was drawing. It's a permeable membrane of thickness 2 millimeters. So in contrast to the way I said it initially, it's not the case that we are just removing the membrane or the interface. There is an interface here, and it has a thickness of 2 millimeters. Right. Another question here in the diagram, are those meant to be straight or curved lines? So in this diagram, the the red line, that's supposed to be a flat line. So that's flat, and there's a discontinuous jump to a lower value. So those are flat lines. The other lines are curved, especially near the interface. So this green here is curved. That's it's not discontinuous to the left anymore. There is a discontinuous jump across here, but here we have a continuous, a curved line. So and as time goes on, the lines become continuous as they meet up here. But initially, the two concentrations were different. So there was a discontinuity initially. Does that cover it? Okay. So there's...
Excuse me, sir.
Yep.
I'm sorry to say, but is there any way that you can change your pointer to something that it is much more clear?
Yeah.
Sometimes I cannot see where you're pointing.
Yeah, I understand. Okay, I'll try and for the next session, I'll be able to set something up. For this one, I'll just try a bit more to make some marks where I am currently. Okay, thanks. Okay, so that's the setup. We actually have a permeable membrane with a certain thickness, and now let's put in some numbers. So in this case, as we said, it's a 2 millimeter membrane. Here we are fixing a diffusivity. And when you work in square meters, you see the numbers get quite small. So don't be surprised at such low diffusivities. Let's see, I think this was a pipeline, so I'm not sure. This diameter is 3 centimeters, that looks like. Really. So anyway, here, this is the differential equation that we are trying to solve here. So at the interface, we have this molar flux. And in our equation, we have estimated this to be the difference in concentrations on both sides. So we can say this is equal to this is going to be the concentration in the first cell of component A minus the concentration in the second cell also of component A, and then divided by the thickness of the membrane, which we'll call delta. Let's just take this down. So this is our estimate of the flux across the interface. And we can see that we have numbers for all these things. So in the problem, we are given the diffusivity. We have the initial concentrations, right? It wasn't given in the original problem, but we specify it as 1 and 5, and you'll see here in the calculation we started at 5 and at 1. So 1 and 5 in the two cells. So these are known, at least initially, and then the thickness of the cell 2 millimeters. So we can calculate a flux as a number here. And then the area of the interface, I guess that's why we needed this diameter here, right? So we have the area of our interface, and we can now estimate, we can integrate this equation. And this equation is written in terms of number of moles. We would rather convert this to a differential equation in terms of the variables that we have here. So what we can do is just divide through by the volume. So if we divide by the volume, we know that the volume is the area divided by the length. So we can divide this and get here C1A, and then this is going to be the area will vanish, and leaving us with 1 over the length of that space. Oops. And this is replaced by this expression. So that's how we can write the balance on the first cell. And you see, you can't solve this equation by itself because you need also the concentration in the second cell, because at the interface, your concentration is changing on both sides, right? The same phenomenon, this diffusion, is affecting the concentration in both cells. So for the second cell, we have to do the same thing. And if you look at it, the same phenomena happen, right? You've got your diffusion flux from the one cell to the other, and you can write the material balance in the same way. So the number of moles in the second cell is changing due to that flux. It's the same area and it's the same flux. It's just the direction is considered to be different. In the first case, if your concentration was high in cell 1, then the flux is from 1 to 2. And then conversely, in cell 2, the flux is into 2, right? So we can write the same balance on the second cell. And we can write it like this. So that's 2, and then we would use a minus in here. So we can either say minus the flux looking in that direction. Well, in fact, that's the best way to do it. So let's just leave it as minus the flux like that. And then we can rewrite this equation as dC2 dt. So we divide by the volume again, and then we get the 1 over L here. So let's just assume both cells have the same length. Right, and so we have the two differential equations. And so that's what this means, right? We have the flux from the one to the other. And if we integrate this, so this part is where we are defining our differential equation block. And then we are using ODE integration over here. And then you get that from the high concentration, it fluxes across to the other one. And from the low concentration, it fluxes into that cell, and they eventually steady out at the same concentration. Right? Any questions or comments on that? Okay, so that's straightforward flux, right? That's how you can do a material balance using fluxes. Now, what we want to consider is that the fluid itself might be in motion. So if the fluid is in motion, then of course we have the bulk flux as well. So we've defined bulk flux before. So we can say the net flux is equal to the bulk flux, or the flux due to the fact that the whole fluid is moving. So the bulk flux plus the diffusion flux. And we know the diffusion flux itself is minus dA dC dx. So you just add these two together. And that's just using the flux notation, the J notation, right? So all that we defined before. Now, what we can say also is that there is another velocity that we can define specifically for component A. So we can say component A is, by the end of the day, there is some collection of molecules A. And if we were to somehow be able to follow just those molecules, then that would define a certain velocity for that component A. So we know we have a bulk movement, right? We know the fluid itself is moving, and that movement involves other molecules as well. So again, let's try and draw a picture around that. So we've got some pipeline. So we've got our pipeline here, and we've got a collection of molecules, and we've got some A molecules, and we've got some B molecules. Let's just say B. So we've got A and B flowing together. And so there exists a certain average velocity of A and B. So maybe this purple line is the combination of the two. So there exists some average velocity, A and B. And then because A may diffuse faster ahead than B. So let's say there was also a gradient across this pipeline. So, okay, let's let A be the red thing, right? So let's say we had a low concentration of A on this side of the pipeline and a high concentration on this side. So I'm pointing here. So here we have a high concentration of A, and here we have a low concentration of A, and that's across the whole pipe. So let's say across the whole pipe, there was a certain concentration gradient in A. So low concentration of A here and high over there. And so overall, we have, in addition to the fact that the whole fluid is moving, we have also that A is trying to diffuse in this direction. So the velocity of A will actually be greater than the bulk velocity. So we can define velocity of A here. So A, and we could specify A in the Z direction, but anyway. And then we can define a velocity here of the bulk fluid as well. And of course, if the bulk velocity is lower than the A velocity, then clearly the B velocity must be lower. So B may look like this. So this might be UB. And it's likely that B is trying to diffuse in this direction against, so B's concentration gradient might be like this, right? It doesn't mean that overall B is moving to the left, right? Because the bulk fluid itself, right? There is a bulk movement. So there is bulk movement of the whole fluid. So that's U. And then there is some diffusion influence. So diffusion influence is, of course, weaker than a bulk movement. So overall, B is moving slightly slower than the bulk, and overall A is moving slightly faster. So the point of all that is that we can distinguish between the velocity of A and the bulk or the overall velocity U. And that becomes important in multi-component mixtures. So there's a little bit here on multi-component mixtures and estimating the convection there. So you can read this. There's nothing really surprising here. So you can estimate the mole fraction on a mass basis. You can estimate the mole fraction and the mass fraction using the molar mass and all the usual things you expect. So that's straightforward stuff. And then here, in your multi-component mixture now, we can define the velocity of A. So this is bulk movement plus diffusion movement that's resulting in our actual velocity of A. And then we can also, of course, we've also defined the bulk movement. Here we are just specifying it's in the Z direction. Of course, we are living in a 3D world. Well, the world we observe is in 3D. And so there is velocity in the X and the Y direction as well, but we are focusing on the Z direction. We are assuming, for example, it's in a pipeline. We are not so worried about velocity in the radial direction or angular directions. And so for now, we are just looking in the Z direction. So there's your bulk velocity and there's your A velocity. And the difference between these, there is a difference between these two because only of diffusion. And so the diffusion flux must equal the difference in the flux that we get overall for A and the flux of A due to convection only. So that's our diffusion flux. So we can replace that by, of course, the expression, the fixed expression for diffusion flux. And then we can rewrite it in terms of CAUAZ. So just taking that across over there. And then we've also said that the average velocity is, right, the overall, the bulk velocity, that's the contributions from the individual velocities. So we can take the velocity of A specifically times its concentration, and then the velocity of B specifically times its concentration. The sum of that divided by their total concentration, that must be how we can get the bulk velocity, right? So that's how you get the bulk. And if you look at this C over C, so that's the mole fraction there. Or rather, no, sorry. Here I'm just saying we multiply by Ca. So if you multiply both sides by the concentration Ca, then Ca over C here will give us the mole fraction. So that gives us now a nice expression that we can substitute for CaUZ. So if we go back up here, this Ca times UZ, we can replace with this thing, right? And so we can say the molar flux of A due to both convection, the molar flux of A is equal to CaUAZ. And so we've said CaUAZ is this thing. And we separate out, so the CaUZ, we replace for CaUZ using this thing. So we substitute this in up here for CaUZ, right? So the CaUZ we replace there, and then we have left over this part. So that's the expression that we get finally for the molar flux of A when you have both convection and diffusion. And you might say, well, can't I just intuitively write down U times C plus dC ddz, right? Don't do that. That's where another subtle error creeps in, because you'll find that you will then lose this term, right? If you try to write this out intuitively, just using convection and convection and diffusion, if you do that intuitively, then you'll miss this term, and that significantly changes our expressions. So once more, this comes from the fact that there are two velocities at play here, right? Convection is defined in terms of only this velocity, the bulk velocity, but actually there is another velocity of component A, and this bulk velocity is influenced by the velocity of component A. So this bulk velocity, we can't pretend that we can just be given this as some bulk number. It is the result of all the species that are diffusing against each other and all of that. So when we take all that into account, we get a different expression than what we might expect. Any questions or comments on that? Okay, and let's take this further. This is just a bit of notation here. So the del notation, that helps us summarize gradients. So instead of saying ddz all the time, we can just say del of x. So del x means ddx of z, and we can also use it for the other directions as well. Don't worry about that too much for now. That's just how we can summarize when we have things in 3 dimensions. Let's just keep working in 1 dimension. And so, okay, well, just read this as ddz of xa. So here we can say that this is now, that we can rewrite this more simply as the diffusion part. So the diffusion part, for some reason, I've written that first. So this is del x, right? So C dAB del x. So that's this term. And then if we look at this term, we can recognize here that this is the overall molar flux of component A, right? So this is the velocity, including diffusion and convection. And so this is the net flux of component A. And by the same token, for the same reasons, this is the net flux of component B. So we can read that as, if you look at this, it's XA times the flux of A plus the flux of B, right? So the XA flux of A plus flux of B. So that's our overall flux. And you can see flux of A on both sides here. So just because our bulk velocity is dependent on all fluxes, we have to solve for A through A itself and the other species. And this is important because it then depends on the nature of the relative motion of all the molecules involved in our mixture. Any questions or comments there? So let's think about some situations there. So let's say we have a component that is in small quantities and it's diffusing through some other component. So let's say this is the solvent component. And we've got our component A, which is diffusing through this. So if component B is not in motion, right, and only component A, so B, let's say B has no gradient, right? So B has a is flatlined. So there's B. And then let's say A has some gradient. So A has some kind of gradient like that. Then we can say NA is non-zero, whereas NB is 0. So in our equation, we can get a more specific form like this. So we can say here that our actual flux of component A, NA, is equal to, so of course the diffusion term, that's still going to be there, so minus C B A B, and then let's just write this as DC A DZ. So that's that first term stays there. But now we've said B is not moving and it's not diffusing on average overall, right? So NB is 0. So then we get this equation. So we get here plus XA times NA. So that's our equation if B is stagnant. And we can now propose to group the NA together. So we can say NA on the left-hand side, we've got a 1 there, and then we can take this term across. So we've got minus XA here. And then on the right-hand side, we've got minus CDAB times DCA DZ. Right, so that is now in a form that we can work with. And that's specific to the situation of B being stagnant. Now let's look at a different situation. Let's take the case where we have a certain surface. So let's say there's a surface here, and let's say components A and B are reacting on the surface. So A is coming in here. It reacts, so this is A. So A reacts, and then coming out is B. So if that's the case, then both A and B are fluxing, but there is there's what's called equimolar counter diffusion. So let's say 1 mole of A goes in and 1 mole of B goes out. Right, so on a basis of 1 mole, we can see there's equimolar counter diffusion. Or we've said this is a reaction. So if the reaction looks like this, 1 of A gives us 1 of B. 1 of A gives us 1 of B. Then would you agree that the molar flux of A towards the surface is equal to minus the molar flux of B also towards the surface. I was careful there. I said B towards the surface because it's going away. So it's minus that, right? So in this case, we have what we call equimolar counter diffusion. So if that's the case, then, sorry, 1 second. Yeah, so if that's the case, Na equals minus Nb, then this is going to add up to 0. And so in the equimolar counter diffusion case, we don't have this term present, and we have simply left over this one. So our equation in this case is simply this one. By the way, I see here there was a little, this should have been an X, right? That's an X, and that's an X. So that was the flow through a stagnant fluid case. This is the equimolar counter diffusion case. So in this case, that's the equation that applies. So you see, it's quite different. And we'll get different results in these two cases. Okay. Now, to solve these equations, there is something a little bit strange we have to consider. Right, so in the earlier case, we had a kind of pipeline here. So A was diffusing through this pipeline. Now, a steady state can exist here. Right, remember in this equimolar counter diffusion case, we said component B was flatlined, so there was no gradient in B, and A had a high concentration here and a low concentration. And that can happen steadily. So it could well be the case that this pipeline is being fed by A at a certain concentration. And for example, A could be leaving by diffusion through permeable walls, or maybe it's reacting on the walls or something like that. So you can get a steady concentration profile across this pipeline. So let's just write separately. It's a bit confusing. It says if we write Ca here as a function of Z, then we could have a steady profile in A, which is not uniform. So A does vary in Z, but it's still a steady non-uniform profile in Z. So as time goes on, we maintain this concentration profile. And that's just because we are constantly feeding A in here, and we are constantly losing A here. So we lose A through the side walls and through the end here. So that's why the concentration of A is dropping. But it's happening equally. The feed of A here is equal to the loss of A through these side streams and the end stream. So it all balances out. And so with time, all of those balance. And so we always get the steady profile of A here. So it's not uniform. At the same time, for this to be steady, it also means that the molar flux has to be steady. So by that, we mean, the molar flux has to be constant, right? So by that, we mean that whatever Z position you look at, the molar flux of A is the same. And that looks confusing, or that looks untrue, because the concentration of A is varying across the space. So how can we claim that the flux is constant? Well, if you look at the flux, let's say we look at just diffusion, just the diffusion part, right? That's based on the gradient of A. So DAV. dc dz, dca dz. So, so if this gradient is perfectly linear, right? If it's a straight line, then the gradient at all these points is the same. And so this dca dz is independent of z itself, right? It's generally not true. dca dz, the gradient of a with respect to z, that is generally a function of z, right? If this was a curved line, right, then the gradient here is different to the gradient there, right? But we are saying now, if the gradient is perfectly flat, then this is a constant. And so our molar flux is constant. So if that's the case, then that's another condition to say that the concentration is going to be constant, right? If you had a difference in molar flux, if the molar flux between here and here were different, then you wouldn't be withdrawing A, your A would not be fluxing out here as fast as it was fluxing in here. And then your concentration must rise. Let's say the flux out was lower than the flux in. Then your concentration of A between these 2 points must rise, right? If on balance you are fluxing more in than you are taking out, then the concentration must rise. But we have said now that the concentration of A is constant in time. So the only way for it to be constant in time is if every single molar flux here is the same. So those are all equal, and then we'll get a constant concentration of A. And so that's why we accept that Na is not a function of Z. So the molar flux is the same at all points across the space. And the reason I'm kind of harping on this point is we want to solve this equation, right? Let's not worry about equimolar counter diffusion for now. Let's stick with that first case. So, so we are trying to solve this case of A diffusing in a stagnant fluid, right? Let's just keep this on one page. So we want to solve this equation. And what concerns us is that we've got all these different quantities and we've got a differential equation. We've got ddz. Now we need to integrate this. And so we need to know which of these variables are going to change in z. So we've just established Na is not going to change in z, right? So by virtue of it, of us being interested in the steady state, right? Because concentration is steady, then this has to be constant in Z. Then in terms of X, well, that's the variable that we are integrating for, so that's fine. The concentration, that's the total concentration. We are assuming the total concentration is fixed here. So for example, it's like if you are looking in a liquid, then that liquid is its density. If the density is approximately constant, then the total concentration is approximately constant. Or if it's a gas and the pressure and the temperature are approximately constant, then that concentration is also constant in Z. So we are not worried about the total concentration changing over the space. We are only worried about A diffusing through the space, and we want to know how the concentration, how the mole fraction of A changes across the space. Diffusivity, we talked about earlier. We said it's a sensitive function of temperature and of the molecules' properties and all of that. And it can be a function of pressure in the case of a gas and all that. So like we just said, none of that is changing. So this is not changing in Z. So everything is constant in this equation except for X and Z. And so we can go ahead and solve this equation. We can separate the variables. We can write this as dx over this. So we can say, let me just put it from scratch. So we can say dxa divided by 1 minus xa. that's equal to, and then on this side, it's going to be NA divided by CDAB. Okay, and there's a minus sign somewhere. And now we can also integrate this, both sides are missing a dz, right? So dz. And if we integrate both sides, then we're going to get here ln. This is natural log of 1 minus xa. And then the limits here are from, we can call it xa1. Okay, my subscripts are not working. So I'll just write it like this, between points 1 and 2. Anyway, let's not write it. And then here on this side, these are all constants in Z. So we can just write this as minus times Z. Right, so that's our equation. And this is between 2 points 1 and 2. So this is between xa1 and xa2. And this is between Z1 and Z2. So we can say the particular solution of this is then XA2 no, quite quickly on this word. And then on this side, it's Z2 minus Z1. Okay, and that's the expression then that tells us how the mole fraction is changing as a function of Z. So instead of specifying an endpoint, we can just say at some arbitrary position Z, we can solve for the mole fraction X through this equation. So that's what you get in the case of the stagnant B, right? And let's see for equimolar counter diffusion. Again, if it's at steady state, your molar flux is constant everywhere. Again, total concentration is fixed, diffusivity is fixed, and so only X is varying with Z. And so this equation is very simply integrated. We can just say this is equal to X XA minus X1, XA minus XA1. Okay, and so you see the situation really governs the way A is going to behave across the space, right? Again, NA is a fixed number. We can solve for XA here. Actually, I should write this as a Z, right? So NA Z times Z. Z. So we can solve for X as a function of Z, and you can see it's linear. So this is linearly related, whereas this one is going to have a kind of exponential curve. So its dependence on Z is going to be exponential, whereas this one is going to be linear. And the only difference between these two cases is that we had equimolar counter diffusion here, and this one had component B stagnant. Any questions or comments there?
Excuse me, sir.
Yeah.
So really quickly, I just wanted to ask, this might be a silly question, but is it important for us to know these equations? Because some of these equations that you're giving us now, they're obviously a little bit different to how, well, a lot different to how you put it in the notes. So I'm just worrying, whether if we will need to use these equations in like a test or exam situation, or they're just for benefit, just to explain further.
You see, when you do these problems, it's not the case that you have to try and memorize this now. And when you look at this page, after all that discussion, this looks like, oh no, how am I supposed to now go and remember all this stuff, right? But if you go back and look at each step, we just went from the one thing to the next. And even the equation that we are using for the whole, the whole basis of this, it's from this one, right? We started here. And if you look at what this equation is saying, number one, we understand Fick's law. We know what this means. This is just writing it, extracting the concentration there. So we know Fick's law. And this is just saying, take the mole fraction after adding up all the molar fluxes, right? So this is the starting equation. And then everything we did after that came from that. What we did was explain the physical situation. So we said stagnant B, so one of those terms vanished, and then everything else was algebra and a little bit of calculus here. Same thing here, right? It's the same equation. Here we just said NA equals minus NB, and so it simplifies like that. So according to me anyway, there's nothing to remember at all. You're just deriving your way through this. So derivation is an important part of this course. And what makes it a little bit difficult, I feel, to teach is it's kind of dry. People kind of get bored while you are, doing the derivations and all that. But what's nice about the course is that it really all comes from very simple statements. Right, this is a very simple statement. There's Fick's law, and then there's the contribution of that component against all the species. From very short, simple statements, it expands into many, specific forms. So you just add you look at your situation, and all you do is customize the general equation. So that's the general equation, and then you just customize it for your situation, and you get the relevant expression. I don't know if that helps in terms of what you're asking there.
Yes, it does. And can you please just go a little bit up, because I think there was an equation or a few equations which I didn't quite get.
Okay, go ahead.
Yeah, it's here, I think.
Did you have a question on these?
No, I just wanted to see something where that last bit. Okay, yeah, right, I get it now. Thank you.
Okay, well, I'm just going to save this in the Dropbox folder, so you can just download this file there anyway. So that's why I like Dropbox. Just while we are talking, things get saved in the space, and I don't have to, try and, we don't need to go and navigate to another space and all that. Okay, any other questions or comments there? Okay, so that's basically how you solve these problems. And if you look at the questions, right, here's one. We had a spherical particle. You are given the radius. It's suspended in B, and we are dissolving. So the particle itself is disappearing in this case. And we want to know what the initial surface flux of A was. So again, you've got a certain mass loss rate. So we are told that the component A has this initial radius. We are also given its density and its molar mass. So we can work out the initial number of moles of A in this particle. We are also told that the particle mass is lost at a constant rate. So we can say that dm dt is constant. And in fact, let's just look at the solution here. So there's your initial mass of your particle. Mass is lost at a constant rate, and we do say that the particle disappears. So that means at t up to 10 minutes, the particle is completely dissolved, right? So that means after that initial amount, after 10 minutes, we've lost the particle. So the total mass that's been lost is m0, and then the time difference is 10 minutes. So that's our mass rate. So our mass rate divided by the molar mass, that will be our molar loss rate. And then initially, we know that the area of the particle is that. And so we can estimate the molar flux there simply in that way. Right, so this one, the way it's posed, you don't have to worry about estimating diffusion or anything like that. Just because we know the mass loss rate, we can estimate the actual flux there. Right, then in the next one, we are given that the fluid, so A is traveling at a certain velocity, and at one position, we know the concentration, and then at another position, which is further along, right? This first one was at 10 millimeters, this is at 30 millimeters. Then we have a different concentration, so a higher concentration. So we are picking up A from somewhere, so maybe from the walls of the vessel or something, but however it's happening, those are the two concentrations. And we are given the diffusivity. So we can use all this now to estimate the molar flux of A, and then we can then we've got the cross-sectional area through which the fluid is flowing, and so we can go ahead and estimate the actual molar flow rate at a certain position. And so here is all of that. So your molar flux is your bulk convection and your diffusion. And so we estimate this part first. So dc dx, just using those two concentrations and those two positions, we get the gradient there. And then we can estimate the molar flux using the given velocity, and we are told which position to look at. So if we are asked for the molar flow rate at that position, 10 millimeters, then we have to use the concentration that corresponds to that. So at 10 millimeters, it's 60 moles per cubic meter there. So we use the 60. So it's velocity times 60. And then we've got the diffusivity that's given to us. We assume that's not changing with the Z position. And then we've just estimated dc dx there. So that's your molar flux. And then you can multiply by the area. By the way, I think this is 4 square centimeters, and somewhere I converted it to square meters. That's why, if you just multiply that by 4, it doesn't look like you'll get that, but it's times 10 to the minus 4 as well there. So, so it's useful to come back to these, all those abstract looking equations. Maybe come back to these problems, and when you work through concrete numbers like this, then it seems a bit more vivid. So you've got that, and then for your tutorial 2, right, that's uploaded to the folder. So there are some nice questions in here. So please work on these using what we covered today. So we've done a couple of examples. You've seen that it changes whether you are in equimolar counter diffusion or whether you are moving through a stagnant fluid. Here's a nice one where you are in counter diffusion, but it's not equimolar. So what do you do in this case? Right, so that's a nice problem to work on. And yeah, basically you can work through this. There is, I think, question 2, estimate the diffusivity, right? So here you're given the correlation, and it's just a matter of looking up these constants. It is useful to have some experience working with these tables. So work through that, and that's basically your tutorial 2. I'll try to turn it into the Publon form where you'll have the solution that you can work through as well. So that's it. Okay, any questions or comments?
So I just have a few questions which I did wanted to ask. It's that part where estimating diffusivity. I understand that that's a new PDF. Is that now the next section, which we have to work through maybe next week or maybe a little bit this week, or is it just something to explain diffusion, which was in our first notes first?
Yeah, it's just a calculation. The way we look at it in this course, it's there are some correlations that you use to calculate diffusivity. So I don't really plan to spend time on it next week. It's more a question of being able to look up in the table for the right thing and calculate the diffusivity. But it's more like just the work of it's just a bit of work to calculate the number. So I don't plan to spend time there. There's nothing really conceptually. It's not that there's nothing conceptually interesting there, but you have to be then going into really atomic interactions, and so that's not what we are looking at in this course. We are looking at momentum, mass, and heat transfer. So I won't spend more time on diffusivity there. So you can read through those notes, browse, look through those notes, see how to use those tables. Next week, we want to move on to the actual material balance. So what we've done so far is just establish molar flux, how to work with molar fluxes, how to compare different molar fluxes in different situations. So the tutorial, work through that carefully. That gives some good insight, some good experience in working with molar fluxes. But next, we want to actually use molar fluxes to derive expressions that describe how concentration becomes distributed over the whole space. So that's what's coming next.
Okay, and just a really quick question. So some of my friends and I have been wondering about this, whether or not, I know it's not on the course outline, but do the tutorials count for any marks, or do they go towards our DP? Does it count for any marks in any way?
So in terms of the official marks, the marks out of 100%, it's all down to the assessments, test 1, test 2, test 3, that covers the 100%. But we are also awarding bonus marks. So you can get a maximum of 10 extra marks on this course. And so these tutorials, completing these extra questions. So in this Publon stuff here, where you see achieve at least 2. So let's think about this. So if you do each of the questions in these Publons and you get your score up over 2 for all the questions, then you'll get extra marks for that. And that 5 is for something else that I explained earlier about, something you can use for your CV. So you get bonus marks for doing these extra problems. So every week, if you do all the questions and get above that minimum number, then you'll get the bonus marks. It's not necessarily all 10 bonus marks. There is something else that we are looking at in terms of there is another activity, which is where you can actually create your own questions so there's a couple of things that we are trying with our teaching and learning. You have to understand we are also trying to evolve our practices and improve our approaches. So it's a bit of a longer answer, but that's what's happening there. Okay, does that cover it?
Yes, sir. Thank you.
Okay, any other questions and comments? All right, if not, I guess that's it for today. See you all next time. Stop sharing, stop.